Welcome to The Explainer. Today we're diving into a piece of technology that is, well, it's absolutely everywhere, but you almost never see it. I'm talking about the flow sensor. You know, from the gas pump you use every week to the IV drip in a hospital, they're the hidden guardians inside countless systems that we rely on every single day.
So this all kicks off with a really interesting question, right? How in the world do you measure something that's constantly moving, something you often can't even see? I mean, you can't just stick a ruler in a pipe to check the water flow. Well, the answer lies in a whole family of incredibly clever devices, and today we're going to break down exactly how they pull it off.
So here's our roadmap for this explainer. We'll start with the absolute basics. Then we're going to open up the toolkit and look at all the different types of sensors, from simple mechanical ones to some really slick devices that use heat and sound waves. By the end, you'll see how each one is basically a specialist, designed for a very specific job.
All right, first things first, let's get down to the fundamentals.
So, what are we really talking about here? At its core, a flow sensor is simply a device that measures how fast a fluid, and that can be a liquid or a gas, is moving through some kind of system. The best way to think about it? It's like a speedometer, but for fluids. It tells us exactly how much is passing by at any given moment.
And you might be wondering, okay, but why does this matter so much? Well, it's a huge deal. Without them, entire industries would literally grind to a halt. They're what make chemical plants efficient, what keep oil and gas pipelines safe, what help us manage precious resources like water, and what let your HVAC system keep your house comfortable. They are the unsung heroes that allow us to control and monitor all these complex systems in real time.
So, let's open up our toolkit, starting with the OG, the mechanical sensor. This is the most direct and intuitive approach you can imagine. I mean, if you want to know how fast something is moving, why not just let it push something?
You can pretty much figure this one out just by looking at it, right? Inside that tough-looking housing, there's a little turbine or a paddle wheel that sits right in the fluid's path. As the fluid flows past, it spins the wheel. The faster the flow, the faster it spins. Simple, physical, and you know what? It's really effective.
Now, the big win for this design is its simplicity and, of course, its low cost. But, and there's always a but, anything with moving parts is going to wear down over time. And if you're trying to measure a fluid that's gritty or corrosive, yeah, that little wheel is going to have a really bad day. So they're fantastic for clean, steady applications, but they're definitely not for everything.
Okay, so what if your application just can't have any moving parts getting in the way? Well, this is where things get really, really clever. Our next tool uses a completely different and brilliant principle: heat. Instead of being pushed by the fluid, this sensor measures how much the fluid cools it down.
What you're looking at here is a thermal mass flow sensor. See that long probe? That gets inserted right into the pipe, directly into the flow. And at the very tip of that probe is where all the magic happens. It actually has two tiny sensors, one that measures the fluid's natural temperature, and another one that's heated to a specific temperature above that.
The principle here is so intuitive. It's just like blowing on hot soup to cool it down. The faster you blow, the faster it cools off. It's the exact same idea here. The flowing gas or liquid carries heat away from that heated sensor. The device measures the temperature difference, the delta T, between the two sensors, and uses that to calculate the mass flow rate with incredible precision.
This method is absolutely fantastic for measuring very low flow rates, especially when you're dealing with gases. That's why they are perfect for things like HVAC systems. The only downside is that their accuracy can get thrown off if the fluid's own temperature or its makeup changes unexpectedly. All right, next up, we're getting into some seriously high-tech solutions. These sensors have no moving parts, and they don't use direct heat. Instead, these sensors ride invisible waves, one electromagnetic, the other sound, to measure flow, sometimes without even touching the fluid at all. How cool is that?
First, let's look at the electromagnetic sensor, which most people just call a mag meter. And that analogy of a tiny generator? It's perfect, because that's essentially what's happening here. The moving fluid itself is going to create an electrical signal for us.
So here's what one of them looks like. Inside that blue body, you've got powerful magnetic coils, and you see the transmitter and display up top. The really key components, though, are those coils and two tiny electrodes that sit completely flush with the pipe's inner lining.
Okay, so here's the physics, and it is just elegant. It's all based on Faraday's law. The coils create a magnetic field across the pipe. Now, as a conductive fluid, and this is critical, it has to be something like water, flows through that field, the fluid itself acts like a wire moving through a generator. This induces its own tiny voltage. The electrodes pick up this voltage, and the faster the flow, the higher the voltage. It's incredibly accurate, and there are no moving parts to wear out.
Now for our second wave rider, the ultrasonic sensor. This one works a lot like a traffic cop's radar gun, but instead of radio waves, it's using high-frequency sound to clock the speed of the fluid.
And there are two main flavors of this. On the left is the transit time method. It sends a sound pulse with the flow and another one against it. The pulse traveling downstream gets a little speed boost and arrives just a little bit faster. By measuring that tiny time difference, the sensor calculates the flow rate. This is perfect for clean liquids. On the right, we have the Doppler method. This one bounces a sound wave off particles or bubbles in the fluid and measures the change in frequency, like a train whistle changing pitch as it passes by. So naturally, this one works best for dirty or aerated fluids.
So what's the trade-off? Well, mag meters are incredibly accurate, but the fluid has to be conductive, so they're no good for oils or pure gases. Ultrasonic sensors, on the other hand, have the amazing advantage of being non-invasive. You can just clamp them on the outside of a pipe, but their performance really hinges on the fluid having the right properties for the job. We have one last sensor to check out in our toolkit, and this one works by deliberately creating a tiny, predictable disturbance in the flow. So let's look at the vortex sensor, and then we'll pull this all together. This is the vortex flow meter, and as you can see, it's built like a tank, and there's a good reason for that. It's designed for some of the toughest jobs out there, like measuring high-pressure steam or super hot liquids in industrial settings. And the principle behind it is just beautiful. See that little wedge-shaped object inside? That's called a bluff body. As fluid rushes past it, it creates this perfectly stable, repeating pattern of swirling eddies, or vortices. It's just like a flag flapping in the wind. The faster the wind, the faster the flag flaps. Same thing here. The faster the fluid, the faster the vortices are created. A sensor inside just counts those vortices, and that frequency gives you a super precise flow rate.
So, the crucial takeaway from all this is that there's no single best flow sensor. It is all about picking the right tool for the job. If you have a simple, low-cost water line with clean fluid, a mechanical meter is probably perfect. For measuring low flow rates of air in an HVAC system, you'd want a thermal sensor. For highly accurate measurement of water, an electromagnetic sensor is the way to go. If you need to measure non-invasively from outside the pipe, ultrasonic is your answer. And for those high-pressure, high-temperature fluids like steam, the vortex meter is your champion.
So we've seen how these incredible devices work, using everything from spinning turbines to sound waves and even tiny, predictable whirlpools. They are truly the hidden guardians that keep our modern world flowing smoothly. So the final question I'll leave you with is this. Now that you know what to look for, where else in your world do you think you'll spot their influence operating in plain sight?